This conference will now be recorded.
Hello folks, my name's Richard Wood. I work for Amy Consulting as a track technical director. So I'm going to talk today about the core Valley Lines, which is a project going on in the Cardiff area. The core Valley Lines is a transformation project that's going on with lines that run north and south of Cardiff, and it's transforming them into a metro style railway network. We had a few requirements laid down by the client who's Transport for Wales at the start of the project. So they wanted 4 trains an hour in each direction on each of the Valley Lines branches. They wanted significant improvements to journey times. They wanted to make reductions to carbon emissions, and they wanted everything, including the transformation and new trains, for a budget of about £750 million. Okay, Sam? So what are we doing? So the approach that we've taken is a whole system approach. So we're looking at the trains as well as upgrading the infrastructure itself. So we bring in 2 new trains onto the network. We're building a brand new depot at Well, and we're making adjustments to Canton Depot, which is based in Cardiff. We're redoubling sections of existing plain line railway. And we're doing remodeling to some of the critical junctions. We're also electrifying the majority of the network north of Cardiff Central. And we're making station upgrades and doing accessibility works at stations. We're also re-signalling the network and building a new control centre, which is going to be located next to Tashwell Depot, and we're introducing a new telecoms network. So just looking at the map on the right-hand side of the screen that you can see there, Cardiff Central is towards the bottom of the screen, just circled in red there. Cardiff Central is on the mainline railway going east to west. Everything north of Cardiff Central sits within is a Transport for Wales asset now, and has been taken off the network rail infrastructure. Everything south of Cardiff remains within the network rail infrastructure. So next to Cardiff Central, we've got Cardiff Queen Street. We've got a short section of railway south of Cardiff Queen Street that goes to Cardiff Bay. The first of the large branches is the Rumney branch on the right-hand side there, and that runs from Rumney down to Cardiff Queen Street. And this will be predominantly used by one of the new pieces of rolling stock that's coming onto the network in a couple of years' time. Just off the Rumney branch is the Corritom Branch, and there's future extension plans beyond the end of Corritom on that branch line. The next branch line is Merthyr Tydfil. The next one across from that is Aberdare. Aberdare's also got the potential to have an extension at some point in the future. The next branch line across is Treherbert. As we go south of Cardiff, say the network south of Cardiff, it remains within the network rail infrastructure. Transport for Wales will be running services on it. The Penarth branch and the Barry branch are the 2 principal branch lines that we're doing work on for the core Valley Lines transformation. Okay, Sam. So I said we were bringing in 2 new trains. They're both hybrid trains. One of the trains is a bi-mode, one is a tri-mode. So hybrid technology is pretty well established in cars these days. So car hybrids use a combustion engine and battery, and we recover energy and store it in the battery from braking and make quite dramatic improvements to fuel economy. The latest plug-in hybrid cars use a battery pack as a primary power source and a combustion engine providing an increase in mileage, and also provides a backup in case there's problems with the batteries. So the same principles are being used in the 2 new trains that we're bringing onto the network. So on the left-hand side there, we've got the Stadler Flirt. So the Flirt is, or a version of the Flirt, is already running on UK railways on the eastern side of the country. On the right-hand side, we've got the Stadler CityLink. The CityLink is a metro-style train. It's also running in the country with a few slight variations on the Sheffield tram system. So both trains have been ordered with a slightly different floor height to standard mainline railway trains at 915. The reason for that was to improve accessibility on and off platforms. They both also come with retractable steps, again, to increase accessibility onto platforms. Okay, Sam. So the Flirt is a tri-mode train. So it'll run off overhead line, batteries and diesel. It'll be predominantly run off 25,000 volt overhead line equipment. And its primary route will be Romney to Queen Street and charging batteries whilst it's running. We do have sections of the railway where we won't have OLE. So one of the largest sections is Caerphilly to Lisvane and Thornhill Station. This is primarily to avoid doing civils works in Caerphilly Tunnel, as they were going to be quite expensive. Once the Flirt train moves past Cardiff Queen Street, it'll go to Cardiff Central and then on to either Penarth, Barry and Bridgend, and it'll run under diesel battery hybrid. Okay, so the second train is the Stadler CityLink, so that's the metro train. Again, it'll be primarily being run off 25,000 volt overhead line equipment on what we call the TAM lines, which is the Treherbert, Aberdare and Merthyr Tydfil branches. It's an OLE battery hybrid, so there's no combustion engine. Again, energy will be saved charging the batteries and the braking. There will be catenary-free sections along the railway. 2 of the largest sections will be through Queen Street Station and Cardiff Central. So the reason for the tram train is its capacity to be able to run on the streets. The current transformation project doesn't incorporate street running. However, there are proposals being developed at the moment to start extending the network into the centre of Cardiff itself. It's likely to be catenary free, and that'll probably require some spot charging during dwell times at stations in the future. But all of that is under development at the moment. Okay, so from a permanent way perspective, one of the largest jobs that we're doing is building a new depot at Tapswell. So this is a plan of the depot. To the bottom of the screen, you can see the main roads, and at the bottom right, you can just about see the mainline railway, which runs from Rada to Pontypridd. So there'll be a new connection of that section of twin track railway into the depot. We've got 32 new point ends in the depot. Those point ends will be quite short tram style turnouts. We used the turnouts that are currently in place on Nottingham tram system and Docklands Light Rail as the template to work off, and then further development with the fabricators. So we've got 10 sidings at the bottom of the screen there, and they're capable of stabling 34 trains. That's more than we're going to start running the service with, but it allows some future capacity for extension of the network. The white section that you can see in the middle is the maintenance shed. So the maintenance shed's made up of wheel lathes, undercarriage cleaner. We've got 3 maintenance roads, one of which has retractable OLE. And then just above the maintenance shed is the train wash. So the whole driver behind the layout of this depot was to allow trains to access stable-in sidings at either end of those sidings to give as much flexibility from an operational point of view as possible. Okay, Sam. So I mentioned we were doing some junction remodelling at some of the critical junctions. Probably the most critical one is Cardiff Queen Street. It's been remodelled again, following its last remodel about 12 or 14 years ago. We're taking out 14 point ends and putting back 17, and that's all driven around achieving the timetables that are required for increased line speeds and 4 trains an hour. There have been quite a few challenges at this location. We're still developing the design, but there's quite a few pinch points with respect to bridges, under bridges through the site. There's a couple of underpasses that go through the platforms themselves or onto the platforms themselves, one of which has very low ballast depth. And the operations guys gave us the target of a minimum speed of 25 miles per hour through all of the new works, which has proved to be quite challenging from a point of view of fitting the S&C units in within the pinch points that we've got and quite a small footprint. Okay, Sam. Another thing that we're doing is introducing new loops. So we've got 6 new loops going in across the network. We've got 4 loop extensions, and we're redoubling the bay line. So all those are driven around increasing the capacity and achieving 4 trains an hour. The entry and exit into the loops typically C to F switches. There is 1 G switch on the Corritom Branch, and that's primarily driven by one of the biggest challenges that we've got with positioning the loops, which is the quite tight reversing geometry, which is the nature of the Valley Lines north of Cardiff. Okay, Sam. So we're doing line speed improvements, more than 30 kilometres worth, spread over 37 locations. We go up to a speed of 60 miles an hour, with the exception of 1 location on the Rumney branch, which is 70 mile an hour. Again, the challenges with line speed improvements have been the tight reversing geometry. We're doing track lowers, 20 of them across the network, and that's in support of installation of new overhead line equipment. The challenges with track lowers have been quite similar to most track lowers across the network. It creates a less desirable vertical geometry, it's created a few headaches from a drainage perspective, and it has driven some more formation works that we hadn't allocated when we tendered for the job. Okay, Sam. So across the network, we've got 114 existing platforms. So eight of those platforms have been extended, and we're building 8 new platforms as part of the works. We're realigning track or adjusting copers in 110 of the existing 114 stations, and that's to create level boarding under the Persons of Reduced Mobility National Technical Specification Notices. And that basically means that we have to work with a maximum horizontal gap between the coper edge and the edge of the retractable steps of 75 millimeters, and a maximum step of plus or minus 50 millimeters. And that vertical step also includes maintenance tolerances, so allowances for track lift and worn rail. And it also includes vehicle maintenance and construction tolerances. And those combined reduce that 100 mil window down to a 25 mil design window, which again is proven to be quite difficult to design around. Okay, at that point, I'll hand you over to Sam Jones, who's going to talk through some of the OLE system that's being built.
Afternoon, everyone. So my name is Sam Jones. I'm Principal OLE Engineer with AME Consulting, based in the south. There we go. So I'm going to talk to you about the electrification of the core Valley lines, more specifically the overhead line system. And I'm going to share with you AME Consulting's approach with the design principles around how we decided we would challenge the core Valley lines. So AME Consulting's carbon emissions reduction hierarchy is essentially to look at the first thing is, is it possible to build nothing? So, can you avoid or prevent? Can you assess what's there? Explore alternative approaches. The next is to look at whether it's possible to build less or reduce what you're building. So evaluate the potential for reusing, refurbishing, or reduce the extent of new construction. Next thing then is to try and build clever. So consider the use of low carbon solutions, different technologies, different materials, possible different construction methods, and again, build efficiently. So again, looking at the construction and the operation to try and reduce consumption of carbon. All of this is in line with the Network Rail environmental and social minimum requirements for projects for design and construction. So what I hope to touch on throughout this presentation is how the core Valley Lines electrification has met this sort of hierarchy. So as Rich has alluded to, the core Valley Lines transformation, as far as overhead lines concerned, we are actually electrifying 2 new depots. What Rich shared earlier with the Taffswell depot, those sidings are actually going to be electrified using rigid catenary. There are then 9 route sections, as Rich went through earlier, with the heads of the valleys, the Tam area, and the Rumley branch, and also electrification down to Cardiff Bay. All of that actually adds up to a total of 170 single track kilometres for overhead line. We are using the UKMS 100 design range, and as Richard touched on, we're using discontinuous electrification, and I'll go through our approach to that. We're using approximately 30 catenary-free section transitions, where we transition from wired to unwired and vice versa. And we also have a total of approximately 60 permanently earthed sections. What we also got is sort of a reduction of the amount of overhead line infrastructure that we need in order to meet the timetable using the rolling stock and the hybrid rolling stock that are part of the CVL. There's approximately 24 kilometres of overhead line that's been installed that is planned to be installed using the permanently earthed section approach, and we're looking at around 81 kilometres of track that we're not actually electrifying. So why discontinuous electrification? The main output of the core Valley Lines was that there was a budget, and in order to try and help achieve that budget, we are looking to minimise the capital expenditure. If you look at historic projects such as GWEP, there was quite a lot of money that went into creating an electrically gauge clear railway. So we've tried to reduce and minimise the amount of civil interventions to bridges, be that replacement or track lowers. However, we've not been able to design them out completely. There's potentially 20 track lowers that are currently being designed, and that is the nature of some of these tight bridges. So how are we doing it? It's a very collaborative system modelling approach. So we have an infrastructure model looking at how much overhead line we are planning on electrifying, and looking at the rolling stock in order to understand the effect of the charge on the battery, to make sure that we have enough charge in the battery to run and provide the timetable service. We are also using best practice from around the industry, using voltage control clearances. So sort of hierarchy, if you like, would be to try and use normal clearances where we can, then reduced clearances, then surge arresters, and then potentially that's when we get down to the permanently earthed section. So the permanently earthed section is sort of last resort, if you like, but it has enabled us to reduce and minimise the civil interventions. Where we then find that we have large numbers of permanently earthed sections backing onto each other, or where we have particularly expensive and cost prohibitive areas to electrify, that's where we look at catenary free sections. I'll touch on those in a bit more detail. And we are controlling the system via beacon control. So the idea is that the trains are automatically detecting when they are approaching a catenary free section or a permanently earthed section, and it's to reduce the driver interaction. Then we're using static charging facilities. So there are at Treherbert and Rumney, there are sidings at the tops of the valleys, as well as the depots at Canton and Taftswell. We're using static charging in order to be able to top up the batteries of the trains. Some of that is using rigid catenary. So what have been the benefits? Where we have complex stations, such as, and when I say complex stations, I mean complex stations for the valleys. We aren't talking Temple Meads or London Paddington, but we have got Pontypridd, Cardiff, Queen Street areas where we've got quite a lot of junctions, canopy, listed status, quite a lot of footbridges, quite a lot of underbridges. So we've been able to currently come up with a system that avoids those areas. We've also got grade 2 listed structures in the valleys. So there's Llanbrara footbridge, Hengoed footbridges at stations, Merthyr Viaduct and Rhondda Viaduct. These were obviously, you've got quite a heavy lot of consents to go through in order to try and attach any overhead line equipment to these structures. And generally, any type of equipment where you're going outside of the normal overhead line foundation, the expense goes up. Caerphilly Tunnel, again, Caerphilly Tunnel was looked at to see whether it could accommodate electrification, but there would be quite a lot of civils works in order to try and get that to a standard such that it would be able to take the electrification. So that's also an unwired area. And then we also have line side EMI interface, so where we're looking to control the electromagnetic compatibility of the system. There are some new university labs at the Cardiff University are building close to the railway, and we have taken the decision to avoid causing them additional EMI interference. Some of the challenges that this leads to, due to the amount of unwired areas and permanently earth sections, we have to cable the feed around those. So there's an increased amount of HV cables going into the system. That then brings its own challenge with potential capacitance issues on the network. We're still doing some modelling around this at the moment, and we may need some shunt reactors, possibly in order to try and help reduce that capacitance. And it gets a little bit too electrically technical for me at this point, but basically during the night, if you've got a high level of capacitance on the system, it then starts to play around with your voltages on your system. And then another challenge that we're all getting used to as an overhead line designer is the new interface with percentage of battery charge. Previously as an overhead line designer, it would be right, you need to electrify from point A to point B, whereas now we've got a new dimension of you have to electrify from point A to point B the most efficient way possible. However, you still need to make sure that you've got enough battery in your system such that you can deliver the timetable. So it's quite a steep learning curve, but it is enjoyable. So continuous free section then. So to try and explain this to you, so this is a wired to unwired arrangement. So we've got our train, whether that's a flirt or an MV unit, and it has a beacon reader on it, and the pantograph on the train is raised. It then passes what we're calling a catenary free section on beacon. That beacon is placed a minimum distance before the end of the wire, such that the train is able to read that beacon and operate the pantograph. However, we have designed a sort of redundant system in should there be a problem with the beacon or potentially the reader, where we're designing the wire height to reach 6,300 millimeters above top of rail. We're designing that position to be at least 10 seconds in front of the nearest obstruction. Idea being that the pantograph would then reach its maximum overheight protection operation point, and then the pantograph will start falling back into gauge by the time it reaches the obstruction. For the alternative arrangement, when you're going from unwired to wired, that's then positioning the beacon such that you've got enough train length where your last pantograph is under the wire, such that when the beacon reader reads the beacon, all pantographs are under the wire. And this is an example of where we're trying to build less infrastructure. Permanently earth sections. Permanently earth sections are not new to overhead line. They've been around quite a while. There's, I think, at least two located on Anglia, the Romford to Upminster branch, and I believe there's also two in Scotland on the Paisley Canal electrification. However, these do need the trains to coast through. So currently, it's a fully electrified railway. They go through an APC magnet and coast through that permanently earth section. And in order to design those, you need to make sure that you've got enough distance between your signals so that you can carry enough speed in order to get through the obstruction, looking at track gradients and things like that. Also, the permanently earth sections that have been installed are based on BICC neutral section, which is 1960s, 1970s technology. It's currently not Network Rail asset policy to fit those types of neutral sections anymore based on previous reliability experience. So I'm not sure how clear this image is on your screens, but to sort of take you through a little bit of the general arrangement. So on the left-hand side, we've got our connection to the overhead line, which is taking the live connection from the overhead line, going down through a HV cable, down through your obstruction. Just after where we're taking the feed is our permanently earthed section insulator. That's actually providing your insulation from 25 kV live down to earth. Then after that, at the next nearest structure, we've got our permanently earthed bonds. So these are the bonds that make sure that the wires are earthed under the obstruction. Then on the other side of the obstruction, again, you've got your permanently earthed connections, again in duplicate. So your and on this right-hand side, we've got another arrangement where we're actually using a bay feeder in order to try and reduce the amount of HV cable and trough route. So the HV cable transitions into a bay feeder, which will then transition to the next live side to continue on your feed around your permanently earthed section. So to take you through the principle of its operation. So we've got stage one. So stage one is where we've got live overhead line infrastructure. Our pantograph is raised. The vehicle circuit breaker is closed, and the traction power of the system is under overhead line. It's approaching the PES on beacon. And you can see we've got our PES insulators, our duplicate earths, and the obstruction. So stage two is it's now past the beacon and it's read the beacon. Your overhead line infrastructure is still live. The pantograph is still raised. However, this time the circuit breaker is now open. So the train is now actually transitioning from overhead line onto onboard energy storage or battery. As the train then traverses the insulator, it's now the overhead line infrastructure is now earthed. The pantograph is still raised. VCB is still open. And now we're fully on battery power. Then as the train passes the second insulator and you're then back onto live overhead line, the train is actually clever enough to detect that that's happened. And after a period of 2 seconds, if the train detects 2 seconds worth of live overhead line, it then attempts to close the circuit breaker. And then finally, you're back onto fully electric power, live overhead line, pantograph is still raised, vehicle circuit breaker is now closed, and you're back on overhead line. So this is an example of where we're building clever infrastructure. So in order to develop the permanently earthed section, we've developed an insulator in collaboration with Arthur Fleury. So Arthur Fleury provide the single rod neutral section, which is currently Network Rail asset policy to fit up to 100 mile an hour. We've been in discussions with Arthur Fleury in order to create effectively a half neutral section version called the single rod element set. This is to try and increase reliability of the PES, and again, base it on modern technology rather than 1960s, 1970s. We're mainly doing this due to the amount of insulators that we will need to install on CVL. What this has brought around is in order to get product acceptance of this, because the CVL network is no longer part of Network Rail, we have to go via product acceptance, and we are going via AMI Infrastructure Wales product acceptance, which is actually very similar to Network Rail's product acceptance process. And then in order to take this product through that product acceptance, we've done quite a lot of dynamic modeling from an overhead line perspective, of the insulator and of the arrangements of how to grade the contact wire on the approach to bridges. We've also done quite a lot of modelling around bridge arm uplift to try and optimise the heights and the minimum soffit heights to try and reduce the amount of interventions. And this is where we're saying we're building efficient infrastructure. So again, going back to some of the challenges, where we're optimizing infrastructure versus battery condition. So we see some charts on the right hand side around some of the results we're getting from the battery modeling. So the modelling of each route for the power demand to try and meet the timetable. So we're getting sort of trip duration in minutes, power demand in kilometres, distance travelled in kilometres. Based on all this information, what it's sort of telling us is that there are potentially areas of the CVL where we have good battery charge, which may start to, you could then ask yourself questions as to whether you need that much infrastructure in that area. And then equally, potentially you're getting areas where your battery charge is possibly at the low end and you might need to put more infrastructure in. So that's what I was trying to say earlier around it's sort of a new dimension for overhead line engineers to get their head around. So finally, a couple of thoughts possibly on how core Valley Lines the approach we've taken could be adopted on future schemes. So the value engineering concept behind all of this was to try to keep to the original budget. So I think the original price at Grip 0 was around about 738 million. And post sort of value engineering, Grip 4, it's around about 800 million. And again, looking at the battery capacity, allowed longer earth sections in order to try and help us keep within 10% of the original price. The smart discontinuous electrification, this could definitely be applied to other electrification schemes. However, the CVL is probably quite a good proving ground for it based on line speeds, and the amount of timetable and the amount of trains and operations that we want to put in there. And it is about an integrated approach. You need the rolling stock in order to be able to enable you to do this. One of the potential benefits of the permanently earth section is that should your obstruction become life expired in a number of years' time, there may be the option that you could renew that civils bridge to an enhanced electrification clearance, which may mean that you can then remove the permanent earth section or possibly reduce the length of the permanent earth section. The one thing that by adding these insulators to the network, there is an increased maintenance cost to maintain them. And then decarbonisation, it's big on the agenda. Building less infrastructure, from a construction point of view and a materials point of view. Possibly that might mean that it makes some electrification of some routes more affordable. And another thing that we're looking at is to try and look into the data from the power modelling. So obviously during design, but also when this system is in operation, trying to look at that and optimise the energy use on the network, and understand whether that means that we can possibly make additional changes to the infrastructure or additional changes to the timetable. And I think that's it. So thanks very much.
We have already a few questions in the chat box. Andy is asking, is switching between modes of operation on the train's battery overhead diesel instantaneous?
I think I'll answer that one. The process that that's been outlined to us in the design documentation is that it's not instantaneous. That's one of the reasons why we are positioning the beacon sort of 2 to 3 seconds in front of the infrastructure points to allow for operation and reading time. So I think it's sort of like around about a second for the train to read the beacon, then potentially another second for it to then tell the control system to tell the pantograph to either disengage, lower, or operate the VCB.
Michael Bradley asked, with the tram-style trains, what would be the estimated time for spot charging?
It depends, I think, on how you try and charge them. I'm aware that Fuller and Frey have a pantograph charging device that would come down and effectively come down onto the train rather than the pantograph go up onto the spot charge. And again, I think it all depends on what type of system is feeding that. Then you've also got the rolling stock itself, in that I think there's a C3 and a C6 charge rate. So quite a lot of it depends on what charge rate the train is ability to take. So there's a lot of variables effectively at the moment. So for example, if you were to take, say, Treherbert sidings, which is an overhead line, with charging statically charging via overhead line 25 kV, and we believe that the trains will be fully charged after about 15 minutes. But for different variables, that may change.
Mark is asking, would there be any obvious challenges with the discontinuous electrification on high speed lines, for example, up to 100 miles per hour?
I think in the development of what we've done, I don't think there would be any larger challenges, if you like. I think the difficulty you have is then it's just dynamic performance. So at the moment, when you put say a neutral section or an insulator in the contact line, you are automatically affecting the dynamic performance of that system and its interaction with the pantograph. And in order to try and control that, you've either got to redesign your equipment, redesign tensions, or potentially look at controlling the line speed in order to reduce the high forces. So at the moment, from what we've done on CVL, we've only modelled up to 70 mile an hour, 80 mile an hour, because that's the maximum line speed we have. That modelling is all compliant to the NTSN for our tension and our system. Obviously, you would have to re-look at that and redo some more modelling at higher line speeds in order to understand whether that was acceptable or not.
Michael Bradley has another question. Michael, in fact, you can switch your microphone on and ask the question directly.
Yeah, no problem. Sorry, it was just more to do with, I think you mentioned that there was approximately 81 kilometers of CFS continuity-free sections. I was just wondering what the scale and size of the batteries required to bridge those sections, and whether you had an estimated sort of scale of those.
I think one thing to clarify is that that's not 81 kilometers of continuous catenary-free section. I don't honestly know the answer to what the size of the train batteries are in the MV unit and the flirt, other than I know that the MV unit is smaller than what's in the flirt. So I'm afraid I can't really answer your question.
No problem. Thanks.
Mark Hambley has another question. You can again switch on your microphone, and I think the same for everybody else. If you want to raise a question now, you can switch on your microphone and ask the question directly to Richard and Sam.
Yeah, it was a question which was it came up on the tram train slide, I think specifically, that there wouldn't be catenary between Queen Street and Central in Cardiff. Is that specifically for the tram trains, or is that in total, please?
So that's in total.
Right, thanks. And is that because of structural issues or?
I think it was a decision was taken early on in the project to try and avoid complex junctions. So, for example, for Queen Street and the Queen Street remodelling, there would be quite a lot of additional overhead line structures and additional overhead line wire runs required in order to essentially take it into account of that, and the fact that we had the hybrid operating mode. We were trying to look at it as a value engineering opportunity.
Yeah.
Now, the battery modelling then also has to support that. However, Cardiff Central is also a bit of a different question in that Cardiff Central is still owned by Network Rail. And obviously Cardiff Central is also electrified as part of GWEP. And you've now got quite a lot of interface issues where if we were to electrify the Valley's platforms on Cardiff Central, and then you've also then got electrification on the Network Rail platforms, you've now potentially got two forms of electrification, and who then takes the lead, who controls it. There's a lot of interface questions that again, if the system can support it, then it was good to try and avoid that.
Great, no, thanks for that.
Can Rich have a question?
I have one. Considering all these optimizations, apparently it's less work for truck, but are there any challenges with this different approach from the point of view of the truck design and from the point of view of the truck installation?
Are you talking about using the discontinuous OLE?
Yeah.
I think from that point, it's had a positive impact from a track perspective, largely due to the fact that we're not lowering nearly as many sections of track underneath bridges as we would otherwise have done. I don't think it's caused us any issues as such, though. Not that I can think of offhand, anyway. We think there's something specifically there.
No, just as a general approach, has this changed in the way the design approach for track was relative to, let's say, the conventional track loading only option or renewal?
Yeah, I think it's really around the track lowering, and it has made a reduction in the kind of drainage interventions that we've had to do as well as a consequence of that. I think because it's a system that doesn't have large sections of non-electrified railway, we're almost working as if it's electrified all the way through. So we haven't taken any sort of further advantages in those areas where there isn't any electrification.
Thank you.
Rich, I've got a question. What design standards are you doing, mate? Using if you've got like SV40s and tram style turnouts in the depot, because obviously they're not covered by 2049, are they?
They're not, no, and we are, wherever possible, we are falling back on Network Rail standards. Where we're using those SV40s, the shorter turnouts and the depot, we're leaning a bit more heavily on Manchester Metro and DLR to get a steer on how we go about doing the design. And we've also leaned a little bit on Stadler, who are producing the trains for us, to give us guidance on what geometry we can work down to. So what I didn't say in the presentation is that we've also got quite tight radii within the depot. It goes down to 25 metres horizontally. But the trains have been designed to achieve that under street running conditions, and we'll only be using the depot for the City Link, the lightweight metro train.
Right.
But you're right enough, it does complicate matters somewhat by using more unusual S&C units.
Yeah, what's the speed on over 25? Well, can't be any more than 10, can it?
We designed it to 10. I think the maximum you can get out of it is 11 or 12, but it's 10 mile an hour that we're operating at.
Right. And it's not continuously checked?
It's not, no.
Oh.
No, we did explore that, an outline design. I can't remember offhand the reason why we didn't do that, but I think it was probably after some visits and conversations with the Manchester Metro guys.
Cheers.
There is another question from Mark. Mark, you can switch on the microphone. You can ask directly as we. Thank you.
Yeah, it was sort of in relation to the same kind of question Andy asked. I know Manchester Victoria tram stop is suffering quite excessive wears on tight curves below like 50 metres. I appreciate the tram manufacturer stated that they can operate to a absolute minimum radius of 25 metres. However, when that gets applied in principle, particularly in Manchester Victoria, the rails after about 3 years started exceeding the not only the maintenance limits but the actual safety limits. So just wondering what kind of long-term issues you foresee arising using that type of S&C.
We have had conversations with the maintenance guys around these sort of issues with respect to tight radii and the S&C that we use in. We're kind of forced down the route of using that style of S&C because that was the pocket of land that Transport for Wales had already purchased for the depot, and there isn't any space on any side of that depot to expand it because we've got the M4 on one side of the depot. We've got one of the key link roads into Cardiff Central, it's the centre of Cardiff on one side, and then we've got a road feeding an industrial units and the main line and Taffswell station itself on the other side. So we're kind of mindful of the fact that we are going to be replacing S&C and plain line more regularly, but to get the trains into the space that we got, we didn't have many options left.
Yeah, cheers, Reggie. I can see it as highly constrained.
Yeah, it's not. In an ideal world, I think we'd have had a much bigger plot and we'd have used conventional S&C, but we'd have needed somewhere probably twice the length. and yeah, probably twice the width as well, I would guess.
Thanks, Rich.
There was a question earlier from Adam with regards to the copy of the presentation, but both the presentation and the recording will be available. The recording will be uploaded on the PWI YouTube channel, and the presentation will be available on the PWI website. If there are no other questions, we'll bring this session to an end. Thank you, Richard and Sam, for presenting today. See you next month on 3rd of November, when we will have a presentation about rail metallurgy given by Andy Franklin.